purpose of this video clip is to explore the role of chemistry in fluid dynamics. So fluid dynamics is a discipline that studies the motion of fluids as well as the interaction of the fluid flow with the surrounding. Fluid dynamics is everywhere in our life, and in fact, for example, hurricane is basically a classical fluid dynamics problem. And if you threw an olive into a cup of cocktail, then you see this beautiful splash, and that is also a classical fluid dynamics problem. And even if we just breathe, then we actually inject a jet into the surrounding air, and that is another classical problem in fluid dynamics. So fluid dynamics can be very useful. For example, design engineers can study the airflow near a speeding car, and that can help us to decrease the drag experienced by the race car, and hence we can make it go even faster. And fluid dynamics can be just also purely fun. For example, we could study the air flows near a running dinosaur and envision how much drag this monster actually could experience at the top speed. And if we have a cup of afternoon tea, we could also wonder what would the flow near a slice of cake if we have a gentle breeze brushing our cake. So by and large, fluid dynamics has been studied and practiced for thousands of years. And most of the time, we focus on microscopic behavior. And it's fair to say that the classic fluid dynamics say neither individual molecules or their interactions. And this can be appreciated by looking at the governing equation of fluid flow, which is the Navier-Stokes equation. So here we show a Navier-Stokes equation for a classic Newtonian fluid. And on the left-hand side, we see the mass time acceleration term. And on the right-hand side, we see the various forces responsible for driving a flow. So now the key thing that you can observe from this equation is that the nature of the fluid actually are entirely encapsulated in two numbers. One is density, and the second is viscosity. So here we really don't see any individual molecules as well as interactions between these molecules. They are all hidden, packed, or encapsulated in these two very simple numbers. This is in stark contrast to chemistry. So in chemistry, most of the time or a lot of times, we are very interested in molecules, right? So how atoms are bonded to each other, and how if we have one molecule here, say for example, a lithium ion that is chelated by a very complicated molecule like this, right? So how their electron cloud actually will interact. So hence, really one key element or key aspect of chemistry that we really oftentimes are looking at individual molecules, their bonding, their interactions, and we care about specificity. And that is, if we have molecule A and we have molecule B, the shape and the size and how atoms are arranged make a great deal. And chemists are very obsessed in studying this kind of thing. And this is actually can also be appreciated by looking at the fundamental equation in chemistry, and that is the Schrödinger equation. So in this equation, both the wave function as well as the Hamiltonian are mostly, right, so people solve them or define them, explore them at a subatomic scale, right? And so here, really, the focus is a lot of time. It's at the kind of the atomic level, right? So here, things are very much oriented towards single molecules, or a lot of time. So now we say that on one side we have fluid dynamics where we really don't see individual molecules, or we don't care about their interactions as long as we get our density or viscosity correct. Well, on the other side, we have chemistry that is relentlessly focusing on molecules and even smaller electrons. So it's fair to say that fluid dynamics has been largely separated from chemistry in the past. So this actually have served us very well. For example, a design engineer, when he tried to optimize the flow near a race car so that we can reduce the drag, right? He or she does not have to worry about the size and shape of the oxygen and the nitrogen molecule, and even less so about, say, for example, the vibration of the atomic bonds. So however, in the past decade or so, a lot of progress has been made in engineering practice that has significantly pushed the envelope of fluid dynamics. And this actually has forced us to take a look at the traditional paradigm where fluid dynamics is segregated from the chemistry. So in a series of videos, we would like to explore the role of chemistry in fluid dynamics. In this video, we explore the importance of chemistry in desalination. So water shortage over the past decade has become a serious global issue. So as shown on this figure that we have here, we can say that a significant portion of the population in the world is or is going to experience serious water shortage. This not only includes countries like Middle East countries where traditionally water is always a challenge, but also other places in the world like California in the United States or South Africa where water shortage is becoming a big pain. So to address this kind of issue, so among the technologies that are being developed, desalination at a massive scale could offer a potential solution. So indeed, one of the appealing ideas would be that if we can somehow draw water from the sea, which contain a lot of ions, but then if we can somehow remove these ions, then we end up with the potable water, and that could really help. So this kind of desalination, among the kind of methods that are being developed, the reverse osmosis is one of the most widely used technology. So in reverse osmosis, essentially what you do is you separate a so-called feed solution with lots of ions and the produced water side using a semi-permeable membrane. So this membrane has very small pores that allow only water molecule to go through, but not the salt ions. So now if you apply a pressure at the feed solution side to overcome the osmotic pressure, then you can drive the water molecule from the feed side to the producer side, end up with drinking water. So technologically, practically, this method can be implemented using this, and that is, we pump water from the feed solution or feed salts through a high pressure pump and then drive this thing through a reverse osmosis module. And through a lot of innovation in chemistry as well as in operations research, so the power consumption of this kind of setup has been reduced very significantly over the past decade. In the 1970s, for 1 ton of water, you need to consume about a little over 15 kilowatt hour of electricity, and this value has been reduced to about close to 2 kilowatt hour per ton of water produced. Nevertheless, reverse osmosis remains a very energy-intensive technology. So hence there is a very strong need to reduce the energy consumption of this kind of operation. So here we can use the classical fluid dynamics to give some idea of how can we do that. If we conceive or if we perceive the water flow through the semi-permeable membrane as a kind of Pursui flow through a round pipe, and that is, if we do that, then the Pursui theory can tell us that the flow rate really scales at the radius to the power fourth, and that is the radius of the pore to the power fourth, and then it scales inversely with the length of the pore. And of course, one have to take this kind of prediction with a grain of salt, because whether the Pursui picture is actually valid here or not, it's actually open question. For one thing, the pore size here must be comparable to the size of a single water molecule, and at this scale, it's questionable that the Pursui flow picture will still remain valid. And secondly, so the classic theory would assume a very long pipe indeed, but here, if the pore is very short, and say as short as a single water molecule, so in that case, again, this equation will may potentially get us into some kind of trouble. Nevertheless, we can still try and say that, well, if we take this idea from fluid dynamics, what can we do to improve the energy efficiency of reverse osmosis? And one of the ideas is to use what we call the graphene as a reverse osmosis membrane. Graphene, as we know, is a single atomic layer of carbon sheet. So the idea here is that if we can somehow dig holes onto this graphene sheet, right, then because of the thickness of this membrane is very small. And recall earlier we said that the smaller the thickness, right, the larger would be the flow rate. And that would really help us to lower the energy consumption per unit mass of water going through this. But there is lots of caveat in this kind of technology, and that is we must make the hole with the right size and the right type of hole. For one, the smaller the pool is, right, so the more difficult it to make, and also it's more difficult for water to pass through. On the other hand, if you make the pool too large, then both water molecule as well ion can pass through. In that case, you don't have reverse osmosis anymore. So this actually points to a fundamental challenge in membrane science, and that is there is always some kind of competition between having a high flux versus having a high solid rejection. So in this kind of scenario, the classical hydrodynamics really is not going to help us too much in terms of designing this reverse osmosis membrane, because the classic hydrodynamics or fluid dynamics doesn't really see a single molecule as a subject of its focus. So in this case, what people can do, what we can study is we can use a little bit of chemistry. And in fact, here we perform a molecular dynamic simulation to study the reverse osmosis. So the key idea here is that we represent both the water molecule, the salt, as well as the membrane with atomic the solution. In another word, right, so we incorporate a little bit of chemistry into our model, and we study the transport of the fluid through the graphene membrane. Shown here on the left figure is when we have a fairly wide pool, right? So below this there are water molecules, but I'm not showing them so that the picture does not get too messy. We say that if the size of the pool is quite large, right? So if we apply pressure, then both water and ion go through, and this is not so good. So on the other hand, if we make the pool a lot smaller, then in this case, we say that after we apply a pressure, only the water molecule goes through, and this is a good thing. And that it produces osmosis, reverse osmosis, and hence drinking water. However, we should be careful about not to make the pool too small, because if the pool is too small, like we said earlier, you would end up with a very small flux. So the question would be, how do we optimize this? Well, one of the ideas that you could do is you can play with the chemistry of the graphene. And that is, you actually can decorate functionalization groups on the edge of this pool. So shown here, for example, we can have two kinds of decoration. One is we have a neutral COOH group decorated on the edge, and in another case, by tuning the environmental pH, we can make these surface groups partially charged. So in that case, we have a charged membrane versus a neutral membrane. Once we have this idea, we can put this into a test. Here what we have is we have a single graphene oxide layer, and on this layer we drill holes and we decorate the edge using a COOH group or COO minus group. And then we put the left chamber with sodium chloride solution and the right chamber with just water. And then we apply a very high pressure from the left-hand side, and we measure the number of water molecules go through this membrane as a function of time, as we showed in this figure. So now from this figure, we can then compute the slope of the water leakage through this pool, right? And that will give us the water flux or the desalination performance. So in this work, what we have done is we tested three kinds of functionalization. In the first case, the pool is 0.68 nanometer in width, and we decorate COOH groups on this edge, right? All these groups are neutral, so in this case, the charge is 0. And in the second step, we realize a deprotonation of half of this functional group, so we end up with 3 charges. And in the last case, we removed all the proton on the COOH group, and we end up with 6 charges. And in all the 3 cases, the nominal size of the pool is 0.68 nanometer. So now once we have this chemistry set up, then we can run a molecular dynamic simulation. And on this figure, what we are showing is as a function of time, how many water molecules pass through this pool. And what we see is at a zero charge, and that is when the functionalization group is neutral, we have a fairly slow kind of permeation of water through the membrane. But when we increase this thing to a -3 electron, and that is now the pool is half depolarized, we see that the slope of this curve gets a lot larger. And if we, however, get to a -6 electron, right? So again, we say that the flux gets smaller. So from this, we can calculate the water flux, right? So what we found is that having a pool that carries 3 electrons, right, actually offers a flux that is nearly 3 times as big compared to what you have for a neutral kind of situation. And importantly, what we found is that for all these 3 cases, so the ions, the sodium chloride ion cannot pass through this pool. In other words, we have 100% source rejection. Through this example, now we appreciate the importance of chemistry, or the functionalization of the graphene, to modulate the transport of water through this, which is classically a fluid dynamic subject. So, and this reminds us again of the importance of chemistry in fluid dynamics. So if you are interested in exploring further the ideas here, and especially why a moderately charged pool actually helps to get the best water flux, you can refer to this paper. So with this, I would like to conclude. Thank you very much for your attention.